I went to computer reset just a few months before the warehouse was cleared out completely. Being so late to the game, I got the VLB board that no one else wanted. This board was on a workbench in the repair room, so pretty much everyone who went there must have seen it, and nobody picked it up. For a very good reason. This Shuttle HOT-419 R1 is heavily damaged by leaky VARTA. We have already repaired the power rail and the keyboard circuitry in another video. If you find this project interesting, you can find the link to that video at the end of this video and in the comment section below. So let's see if we can repair this unwanted board. This board is going very slowly through the post codes and gets stuck at 13. Unfortunately, the information I have found online about code 13 isn't very conclusive. However, the board also beeps 3 times, which indicates a memory problem. We have tested the board with freshly tested 30 and 72 pin SIMs. The CPU is tested and all jumpers are correctly set. Before we start the repair, we need to test something. As a viewer kindly pointed out in the comment section, the extremely slow post attempts might be caused by a lack of a turbo switch. We have actually seen this before in the Commodore 486 project, although I can't recall it being quite this slow without a turbo switch. Let's find out. Let's see if this made any difference. No, this is extremely slow. There is no way it should be this slow. No, I'm skipping ahead here, but this is taking forever. I'd say about 1 minute to get to postcode 13. So we either have at least one more fault with this board, or some bad traces going to the RAM are somehow making this board very slow. We are of course going to check the frequency with the scope later. So the reason why I couldn't continue this project in the previous video was because I didn't have a Dremel. So I went ahead and ordered one. That means we can use one of these green rubber polishing tips to remove the solder mask of those damaged traces. The board is damaged from roughly this point here, and then the battery juice went all the way to this corner here. This edge here is mostly fixed now, all the way past the power connector here. So today we're going to focus on this edge here. The board looked like it might have damaged traces underneath this SIM slot here, and underneath at least 2 of these cache sockets here. So we need to remove them to get access to those traces. We've got roughly the same thing going on this side here. The corrosion starts here. It goes all the way down to this corner, then along this edge here, up until this resistor pack here. So far we only have 7 broken traces. But it's very likely that we have at least one more broken trace, affecting the memory here. Only the 2 first rows of cache sockets have visible damage, so it should be enough to just remove 4 sockets. But first, some flux and some fresh solder, at least on this first row here, that is clearly corroded. I'm skipping the flux and just adding some fresh solder to the remaining pins to make the desoldering quicker and easier. Yes, this is totally working. I try not to push with the desoldering gun because some of these traces may be a bit fragile. Yeah, this is working really well. Only a few of these pads gave me trouble, so I'll add some fresh solder and have a second go with the desoldering gun. Still a few stubborn pads, so let's try with some flux and some more fresh solder. No, that solder still won't come out from a few of those through holes. So let's heat the board up with the heat gun for about 30 seconds and try again. Yes, that did the trick. So all the solder is out from all the through holes. Some of the pins were bent, so I checked every single pin and made sure they are all straight. These sockets are of course still stuck, so let's use the Rework station and melt the remaining solder. This board obviously has a very large ground plane. Being this stubborn, I'm skipping ahead here. Those pins are coming off very slowly. No, this is taking too long. If I keep heating this area, the board will get bent. So I'll use the heat gun and heat the entire board up before I continue. Okay, the board is nice and toasty now. Let's try again. Okay, there we go. Finally, I'll do a quick inspection and reheat the entire board before I grab the next socket. Okay, all the pads look fine, and I reheat the entire board with a regular heat gun for about a minute. So simple thing like this sometimes take a very long time, and if done in a hurry it can create a lot of damage to the board. I am pushing on that socket very gently with a screwdriver, making sure not to use any force. I am of course skipping ahead here. This is taking its time. Now there's our next socket. Okay, I use the same method on all 4 sockets. Let's clean this flux up with some IPA and make an inspection. Okay, I did an inspection and this doesn't look too bad at all. All the pads are fine, but I obviously still can't see if these traces are okay or not. So that will be for the next step. But first, we need to remove this SIM slot here. Now let's see what we will find underneath this corrosion here. I think I'm gonna replace these 2 caps, just to make the cleaning process quicker and easier. Well, it's hard to tell before we have used that polishing tip, but all the pads look fine, and the corrosion seems to stop underneath this socket here. So we can leave the remaining sockets in. Okay, so this is the most likely part of the board where we will find our break. There are some empty pads here, by the way, for 4 additional 30-pin SIM slots, instead of those 2 72-pin SIM slots. I'll add some flux, at least to this slot here, and then some fresh solder to all the pins. Hopefully the flux has done its magic. Yeah, this is totally working. Okay, I had to reheat the board a few times because there are a lot of pins here, but now all the solder is out. So let's use the rework station to make sure all the pins are unstuck and pull that SIM slot off the board. Well, it's not coming off quickly, that is for sure. Yeah, I'm gonna need to preheat once more. Okay, board preheated again for about a minute. Let's see if this is enough. I'm just very gently pulling on that slot. I'm not using any force to avoid damaging the pads. I'm actually skipping ahead quite a lot here, but it is coming off just very, very slowly. No, that is taking too long. I'll preheat again. What a stubborn board. Okay, let's try again. Okay, I think it's coming off now. Finally. There's our slots. So let's clean this up. Do an inspection. It's so much easier to clean the flux while the board is still warm. So I do my cleaning right away. Well, all the pads look fine on this side. So how about this side? Yeah, I think we're okay. All those pads look fine. Underneath that crusty corrosion, I think the corrosion stops here. So we'll leave this slot in, at least for now. I decided to remove a few caps here too, just to make the next step easier. And the next step is to clean all the traces and tin them, to expose any breaks. As it is now, we can't even see these traces. The reason I couldn't do this in the previous video is because I didn't have the proper tool. But now I do. I got myself a Dremel. However, the Dremel is way too big for this type of work. Those traces are hair thin. So for this job the Dremel is massive. But I got mine with a flexible shaft. The flexible shaft is still quite a bit larger than my old tool, but this should be good enough. Together with the Dremel, I also got these green rubber polishing tips. So the main idea here is to clean off the solder mask without damaging the traces. I'm not going to practice on our board, so I grabbed a random scrap board here. Apparently, I think I managed to grab a board manufactured in the same year as our motherboard. So let's give this a try. So let's try this at half speed. Well, it's a bit noisy, so that's not great for a video. But it seems to work really well. Well, I won't know until I edit how noisy it gets on camera. Oh, used at an angle, it's actually not as noisy. Yeah, this is much better. And it works great. Okay, that's enough practice. This tool is obviously great and perfect for the job. It does get a bit dusty, but the result is perfect. This is exactly what we need to do with our board. While practicing, I noticed that it went through the outermost layer of the PCB quite quickly. So ideally, I would prefer polishing tips with finer grain. I'll see what I can find for the next project. For this board, I'm just gonna go very slowly and be very careful. And perhaps even use the microscope. But this is totally working. I hope it's not too noisy. I think I'll do a partial edit and find out how noisy it is before I continue. But as you can see, this is totally working. And it's working really, really well. I should have bought this tool years ago. Okay, I'm done cleaning here. The good news is that the tool is great. It did exactly what I hoped it would. So now all the traces and the breaks are clearly visible and should be possible to fix. On this side here, we've got the bad news. I still think the board is fixable, but it's way worse than I thought. There are so many traces underneath this slot here that have breaks, and along the edge here quite a few traces are more or less missing. So I thought this project was tough, but this is even worse. So the next step is to tin all the traces. The tinning process is quite straightforward. Tons of flux and a tip with a large flat surface. A splash of solder. And then we can let the flux do its magic. So this is the easy part. Since I found so many broken traces underneath Sim 8 here, I decided to remove Sim 7 and have a look underneath. But I can't see any breaks. To give myself a fair chance to actually make some progress here, I'm going to skip these 2 Sim slots for today. 4 slots should be enough for this project. And if I ever change my mind, I can always install 2 slots here. That also means we can place bodge wires on this side of the board too. It's not going to be pretty, but this is not a pretty project. So let's start repairing traces. We have a few to fix. So this, I believe, is ground. It is. And we've got this trace here, probably going here. It is. Then we've got this trace here. This one is okay too. And here's our first break. This entire piece here is completely missing. So let's fix it. Okay, short bodge wire cut to size. Yeah, I have decided to embrace that this project is a bit rough and ugly. This is gonna save me some time. Okay, let's check the next one. That's good. This one too. So I'll skip ahead here until I find a break. It didn't take long. This pad here has traces in both directions. This trace here goes in under this slot here. I obviously don't have any schematics for this board, so I'm just gonna have to poke around and see what I can find. Then this pad also has a trace going in this direction here, and then we have a break here. I'll double check with the microscope, but from what I can tell it's going in this direction here and should connect to this pad here. I'm making some of these wires way too long intentionally, because we may have to solder wires to these pads too, and I need to be able to move this wire around. We'll glue them down later. Okay, let's check again. Yep, that's fixed. And this trace here also continues to this pad here. I realize of course that we won't need all of these pads connected, since we're not going to use 72-pin SIMs. But it's much quicker to just fix them all than finding out which ones we need. Our next broken trace is going from this through hole here, and we're supposed to go up this way and connect to this via here. This via has a trace on the other side of the board going to this pad here. So I'm gonna route a bodge wire from this through hole here to this pad here underneath the board. I hope it doesn't get too crowded on this side of the board. So let's check. This pad here should go to this via here. No, it does. I think I briefly forgot to turn the microphone on. If I did, we just connected this pad here that has a trace going all the way to the edge here, and then it's broken. It's then going in this direction here, and it connects to this pin on this resistor pack. So that one is fixed, and now I just found another one. So this pad here also has a trace going in this direction, and it's also broken here. It's going to this via here. On the other side of the board it's going to this via here, and then it connects to this pin here on this resistor pack. Okay, let's add a second wire to this resistor pack here. In case I didn't have a microphone on. This is how we're doing so far. I decided to finish this area off camera, because the remaining breaks were very similar to what we have done here. And I checked this area here, and everything seems okay. And I moved on to the cache area here. And for about half an hour I thought this was the end of this project. These traces here are really bad. But I was able to see where this trace here connects, and these two traces here. But this innermost trace here turned out to be pretty impossible. It could have been connected to any of these pads here. So I went online and checked tons of images of similar boards, but couldn't find anything that would reveal this trace here. But then I checked some pictures in my camera, and I was able to identify where this trace goes. So we're back on track. We're gonna fix these traces on the other side of the board. So to have something to solder these wires to, we need to install some sockets. I have removed the solder from all the through holes. I'm gonna go with shorter sockets, because this is the type of cache I'm going to use anyways. I'm gonna solder 2 pins roughly in the middle of each socket, and then make sure they are straight and sits flush to the board. And then I'm going to solder the remaining pins. Since we don't have a solder mask in this area, I'm gonna have to be careful and make sure we don't bridge anything. Okay, sockets are soldered. I cleaned up the board and checked for bridges. And of course there was a bridge. So be careful when you solder something on a board that is missing a solder mask. It's very easy to bridge 2 traces. But that has been fixed now. So now we need to connect these 4 pins here to these 2 vias. One via hidden underneath this socket here, and this pin here. By looking at my old picture, I have also checked all the vias underneath these two sockets, because I knew we wouldn't be able to check them now. And they're all fine. Oh man, this is bad. This is probably the worst area on the entire board. There are at least 10 broken traces, just in this area here. So, to give myself a fair chance to upload on time, I'm gonna skip ahead here and just do a whole bunch of repairs here as quickly as possible and skip ahead here.
Many hours later.
Well, that was a pretty good guess. There are in fact 13 bad traces just in this area here. So all in all, we have repaired 25 traces on this board so far. We still have 2 more to go, but they are in the CMOS battery area, so I don't think we need them to post. That means we are ready for a test. But first, a quick correction. I was referring to the 0-ohm resistor as a fuse in the previous video. Luckily several viewers corrected me in the comment section. That is in fact the 0-ohm resistor. I just assumed it was a fuse because on the silk screen there is a symbol for a fuse. But apparently the manufacturer cheaped out and used the 0-ohm resistor instead of a fuse for the keyboard. So I better never get a short in my keyboard when using this board. Let's add some freshly tested RAM in the remaining sockets. A power supply, a graphics card, and a post card. Okay, I'm a bit nervous now. I deliberately don't count the hours I put on a project like this. But your guess is probably right. So, let's see what this board will do now. Fingers crossed. Okay, we had something on the screen. We've got 0C, 0D. It's still very, very slow. 0F, 10. I am skipping ahead here, but this is extremely slow. 11, 13. What? 14! Oh no, I think it started over. Did that board just reboot on 14? Let me loop this and see what's going on here. Oh no! It got stuck on 13 on the third reboot. It went to 14 and then crashed. And on the third reboot it got stuck on 13 and now it's beeping. I think there was 6 beeps. Let me double check. Okay, I checked and that was in fact 6 beeps. So that is actually great news. Because that means it goes past 13. So that means the RAM is now okay. But as soon as it reaches 14, the whole system crashes. And I think it reboots. Okay, after that crash, it got stuck on 13. But it still gives 6 beeps. And 6 beeps is the keyboard controller. Let's add a keyboard and see how it behaves. Not likely to be different, but let's give this a try. Yeah, so as soon as it reaches 14... Oh, it posts! The board posts! Holy crap! Why did it crash the first time? That messed up bloody board is actually posting. And the post code reached 85 now. So what the heck? What's going on here? Well, we obviously still have some things to fix. So we've got CMOS battery state low, of course, because we don't even have a battery. And CMOS display type mismatch. And the keyboard interface error. I think I might know what's causing this keyboard error. But hey, let's try F1. Why not? No, that doesn't work. So the keyboard circuitry isn't working at all. But hey, it posts! This is a huge win for this project. Apparently it has the BIOS for the R1.1 version of this board. But this is actually an R1 board. But hey, this is a huge win! This board is actually posting. But we still have 2 issues. So the keyboard circuitry isn't working. And for some reason this board is running very, very slow. At least during the post. Let's reboot and see if this is consistent. I am skipping ahead here, but it is consistently slow. So it crashed and then started over from code 6. And on a second attempt, it posted very quickly. So something is holding this board back. But after that crash, it seems to behave normally. Let's pull that jumper off the turbo switch. And boot again. Yeah, exactly the same behavior. So as soon as it reached 14, it crashed. And then started over from code 6. And then it very quickly went to 85. And the system posts. While I was editing the previous video, I noticed that I had missed one trace. So this trace here is going this way, and then it's going nowhere. I had a look at the board. First we have a spot here for a few pin headers. They are not mentioned in the manual, so I don't know what they do. And then we also have this via here that is going absolutely nowhere, because this area here is so badly damaged. I can't even guess where it's supposed to go, but most likely to these batteries connectors, or the pin headers here, or perhaps to our missing trace here. So we can't guess, because then we might damage something. And this board has seen enough of damage. Let's find out. If we check this trace here, it's going to this via here, on the other side of the board. This via is going to this pin here. And that pin is pin 6 on the keyboard controller. So very likely our issue here. So let's check on another fully working 486 board. I have pulled the keyboard controller out of the socket. So let's check pin 6. Pin 6 on this side of the board is going to this pad here. On the other side of the board there is a trace going to this via here. And this via is going to this pin here, and that pin is this pin here on the BIOS chip, but it's also connected to a very long trace going all the way down here and connects to via here. On this side here it's coming up underneath the 85C471, but if we check these pins here, there it is. So now we know where pin 6 should go on the keyboard controller chip. Here's our trace, and it's going all the way up to this pin here. If we turn the board around, that is actually the same pin as on that working board. So that's enough for us to know that we are on the right track. But let's follow the lead. Back on this side, that pin is also connected to this via here. Now this via here has a trace going to this via here. On this side, that via has a trace going to this via here. And you guessed it, of course. It's coming up underneath the 82C895. And it's connected to this pin here. So that is definitely the missing via for our trace. The easiest way to fix this is to add a wire to pin 6 on the keyboard controller and to the pin of the BIOS chip. So now we should have a connection between that seemingly unused via and this trace here. And we do! Okay, so that's fixed. By the way, this combination of motherboard, graphics card and display gives me this thin blue line when the motherboard is turned off. That's a first for me, never seen that before. Okay, fingers crossed. Oh, jump directly to 14. Yes! We fixed it! That post only took 1 or 2 seconds. Okay, let's try F1. Yes! It totally works! Let me see if I can fix that refresh. No, apparently I can't sync this refresh rate to my camera. So let me show you how quickly it posts now. Turn the machine off and on. Yeah, no skipping ahead, so just a few seconds. This is awesome! We fixed that board with no less than 25 broken traces. But VARTA is not getting this board. Okay, let's install a hard drive in this funky BIOS. Mouse support without an OS. This BIOS is magic. Okay, I can't find my hard drive in this list. So I'll just enter these numbers manually. Okay, let's try this and see if it boots. Oh, it has auto detect. But that is actually the incorrect information. So it didn't guess right. I guess that feature isn't great. Save changes and exit. Not sure what's on this drive or if it's even working. But I guess we'll find out in a second. That didn't work too well. Okay, apparently this board won't boot without the CMOS battery. By the looks of it, it seems to take several different types of batteries. If I'm not mistaken, these pads here are actually for a Dallas battery, or at least something similar. But I'm gonna go with the CR2032 standing up. We could use a regular holder, but then it's poking out slightly from the board. And I don't know if it will fit in a chassis. So let's play it safe with the coin cell battery standing up. That means I'm going to bend one of the leads like this and solder it like this. By the way, this board requires a jumper on these pin headers here for the circuitry to connect to the battery. Not sure what it's for, but probably has something to do with the Dallas battery here. So I'll solder the diode on the negative side. If you're all new to this craziness, the diode is here to stop the motherboard from charging the CR2032. I have been experimenting with rechargeable 2032s, but I have been advised not to use them because apparently they are a bit picky with the charger. So apparently it's a bit risky to use those batteries on an old 486 board. I decided to add some Kapton tape between the through hole and the diode lead, just in case. It's not really touching the lead, but just in case. Okay, let's try this. So this is the positive side of the battery. So current flows in this direction when charged, and the diode here prevents it. Oh, we might as well replace the caps we removed earlier. DC14 here is a 10 micro 16 volt tantalum cap, and the remaining 4 caps are 100 nanofarad ceramics. I use regular caps and bend the legs to make them fit. Not the easiest thing to solder in this crazy mess of wires. I also have to be very, very careful not to bridge anything, since there isn't any solder mask left on this board. It's so easy to do. If I just touch one of these traces here, they will immediately short. I should have replaced these components before I repaired these traces here. Okay, let's see if this works. F1 and the magic BIOS with mouse support. I grabbed a slightly larger hard drive. Let's try this auto detect again. I'll just set a random date. How about 1994, when this board was made. Cache memory bad. Do not enable cache. Okay, interesting. And we've got an A: drive error. Okay, 66 MHz CPU clock. By the way, we don't have any cache chips on the motherboard, so hopefully that was the reason for that error. It's also set to have a 360K drive and hard disk type 47. Okay, let's try with a different hard drive and a diskette drive. Okay, it seeks and it reads from the diskette, but it shouldn't be, because we haven't made a change in the BIOS. That created some confusion for the motherboard. I'll reboot. Okay, so we should use delete during the post. Okay, we're in BIOS. Floppy A 1.44 auto detect hard drive. Okay, it doesn't boot from that hard drive either. Let's try the diskette drive. Starting MS-DOS. Yes, it's working. So let's exit and run fdisk. Display all partitions. Well, here is our drive. Apparently it was used by someone called A. Davies. This hard drive is from Computer Reset 2 actually. So it will probably stay with this project. Now let's try to boot from the hard drive. Missing operating system. Okay, so A. Davies apparently cleaned his drive before he sent it to Computer Reset. I decided to swap that hard drive. This is the original hard drive that came with my PS1 desktop. If I remember correctly, it still has DOS and Windows. So let's run auto detect again. Yeah, I think that might be right. Starting MS-DOS, yes! It boots from the hard drive now. We even have mouse drivers. We've got a PS1 splash screen. This is most certainly not a PS1. And it crashed because it's running Cirrus Logic drivers. I guess I could just swap that graphics card, but let's not. Oh, we've got some benchmarks on this drive. Let's try SpeedSys. This should give us an indication whether this board is stable. This display is absolutely tiny, so even I have a hard time reading. And SpeedSys seems to run at a much higher resolution than this display is made for. It will work, but it doesn't look great. And we're getting an incredibly low score of 5.86. So something is wrong here. Let's try with a jumper instead of a turbo switch. Now let's run these tests again. Well, I think the test is running much faster now. Now we're getting 24. The DX266 is not in the list here, but it's slightly faster than a DX250. So a bit slow for a DX266. But then again, we don't have any cache chips on the motherboard. Well, I guess that's the next thing to try. But first some deoxit, because I'm going to test with the original chips that came with this board. And they were a bit crusty. These are 32K by 8. So they should give us 256K. But I think this board can take 512. When do you actually need 512K of cache? Aside from using deoxit, I also cleaned all the legs of these chips with an abrasive pen. And then I pulled them in and out of the socket a couple of times. And hopefully that will scrape off any corrosion left. Okay, let's try this. I have also swapped that graphics card for a Cirrus Logic. Okay, let's get into advanced setup. And enable some cache. Save changes and exit. And boot. Oh no, it doesn't work. Well, hopefully that's just a bad cache chip. Okay, I found a full set of cache. And they are freshly tested on another board now. Okay, the freshly tested cache is installed on the motherboard. With some more deoxit. In case this is an oxidation problem. Okay, fingers crossed. Oh no. It doesn't work. Something is wrong. I was poking around with a scope in the cache area. And this guy came right off. So I definitely need to glue these wires down. But that is kind of a last thing to do. Well, it's back on the board now. I think I have the cache disabled in the BIOS. Yes, it's disabled. So let's enable it. Save and boot. Oh yes! I think it works. No way! It went past very quickly. Let's check. Okay, the benchmark gave me some trouble. So I installed some more memory. I can't even see the memory in here. Oh, why does this happen? I just want to know if it works. And then I get this crap. But you guys probably know, since I made that splash screen visible when I edit this video. But I don't actually know if it runs. I think I saw 256K flash by. Well, there is nothing about the RAM inside here. What a strange BIOS. Let's boot and see what happens. I've upgraded from 4 megs. Yes, definitely says 256K cache memory. I think we finally fixed it. Let's confirm this with the benchmark. Okay, let's try again with SpeedSys. Here goes. 8K of cache. Here it comes. Yes! Yes! We fixed it! We've got 256K of cache working on the board. Screw you, VARTA. You ain't getting this board. If you ever wondered why anyone would take on a project like this, well, the victory feels pretty damn good right now. The unwanted VARTA VLB board that no one else wanted is now finally fully working. We are of course going to overclock it beyond its limits and put it in a very suitable case. I also have some unusual plans for this build. More on this later. If you're watching this in the future, there will be a link to that video on the screen shortly. If you're watching this fresh, hit the bell icon below and set it to all to get a notification when the next video is out. And now is a good time to watch part 1 of this project if you haven't watched it yet. I will end this video by saying thank you to my patrons. I appreciate your support. If you want to support me too, consider becoming a patron. Patrons get ad-free early access whenever possible. If you want to help me make more videos like this, like and leave a comment. If you are a regular viewer, consider subscribing to this channel. Thank you for watching, I'll see you next week.